Okay, 2.8 is the related rates problems here. So related rate problems is what we're going to solve. These problems where you can find the rate of change for one of the variables without knowing the rate of change for another. So you can't find the rate of change with one without knowing the rate of change of the other. So if I'm talking about, let's say, a balloon, okay? Let's say it's completely spherical, so it's a complete like circle, okay? It's not going to be like egg-shaped or something like that, okay? So yeah, so it's not a usual balloon. It's a very high-tech balloon. Okay, as I'm pumping air into that balloon, can I be pumping air in at a specific rate, like so much air per second or whatever, right? Yeah, which is what most like things are going to do, right? Now, isn't the radius going to be changing as I pump air into this balloon? Yeah, and I might be able to measure how much that is changing, right? Isn't the volume also going to be changing? Okay, so there's all these different rates of change going on. Okay, I can measure some of them. Some of them are easier measured than others are. So maybe one of them is super hard to measure. You can still calculate what it is if you can measure a couple of the other ones using an equation. Okay, so those are the type of problems that we're going to be doing here. So as an example, suppose the path of a particle can be modeled by this equation. If you think about the velocity as it moves along the path, there could be a horizontal velocity and a vertical velocity, and you can take the derivative with respect to time to find that. So, you guys ready? Do you guys remember implicit differentiation? Very last section. Okay? When I took the derivative of y, what did I need? A dy dx, right? When I took the derivative of x, did I need anything like that? No, because I was taking the derivative with respect to x, okay? Now for 2.8, we're going to be taking the derivative with respect to time, with respect to t, okay? So if I take the derivative of a y, instead of dy dx, what am I going to put with it? Dy dt. And if I take the derivative of an x, I'm going to need a dx dt, okay? So every time you take the derivative, you'll have like a d whatever dt. It just depends what the question's asking you to solve for, okay? So let's just try this first one here for an example. So if I take the derivative of y, the derivative of y is 1, and then what do I need with it? dy dt, thank you. What's the derivative of x cubed? 3x squared, and then I need a dx dt. Good. And then the plus 2? 0, so it just goes away. So this would be what my dy dt equals, okay? Now, a lot of times they'll give you a dx dt and an x to plug in, like this example, but we'll do that down here. Okay, so this derivative demonstrates that dy dt and dx dt are related rates. They relate to each other. You cannot find the value of dy dt without knowing dx dt and vice versa. So let's try an example where we're given something to plug in here. So first thing we want to do, same idea as what we did up here, find dy dt. So first I want to take the derivative of this. And then I'm given x is 1, I'm given y is 3, and I'm given dx dt is 6. So after I take the derivative, you plug these in. So plug in after taking the derivative. Yep, after taking the derivative though, okay? So let's try the derivative. What's the derivative of the 2x squared? There we go. Plus, there you go. And then we're going to plug numbers in here. So I know my x is 1, so I'll be putting 1 in there. My dx dt is 6, so I'll put 6 in there. My y is 3, and what I'm trying to solve for is my dy dt. So this I have 4 times 1 times 6 gives me 24 plus 6 dy dt is equal to 0, and then just solve. So subtract the 24. And then divide by 6, so I get my dy dt as what? Okay, so questions on that? You can move stuff before you plug it in if you want to. Yeah, and sometimes people do that. Like sometimes at this step, people solve for dy dt, and so your dy dt would be like the negative 4x dx dt divided by 2y, and then you can plug stuff in. Either way, you get the exact same answer, okay? I usually just like to plug it in right away because numbers are easier to move around, I think, for some people than variables. But any other questions there? Okay. So now we've got some story problems here, okay? And this will be a lot like your homework. Like your homework, you'll have a couple problems that are like that first example, and then you'll have more, story problem type things. Okay. So there's a couple things that I write down for every single problem just so I don't confuse myself. I write down my known, and I write down what I'm trying to find. So if I'm looking at number 2 here, it says, pebble is dropped into the calm water, causing ripples in the form of concentric circles. That just means the circles have the same center. Okay, the radius of the outer ripple is increasing at a constant rate. Uh-oh. There we go. Is increasing at a constant rate of 0.75 feet per second. Is this going to be positive or negative? The 0.75. Positive, why? Because it's increasing. So if it's increasing, it's positive. If it said something was decreasing, you'd have a negative rate, okay? At what rate is the total circumference of the outer circle changing? So this is what I know, right? And this is the rate of change of what? No, the rate of change of the radius, right? So if it's the rate of change of the radius, instead of like dx dt or dy dt, I'm going to call that dr dt. Okay, it's the rate of change of the radius with respect to time. So I know my dr dt is 0.75. And I'm trying to find the rate the circumference is changing. So I'm trying to find dc dt would be a good label for it. So first thing I have to do is I have to come up with an equation that relates radius and circumference for a circle. So how do I come up with the circumference for a circle? You're both wrong. 2 pi r, there we go. So my circumference is 2 pi r, so we write that down. Then what do I do with it? I can't plug it in until I do what? Derivative. So I'm going to take the derivative, then I'm going to plug my stuff in, okay? So if I take the derivative, what do I get? The derivative of c would be dc dt. 2 pi is just a number, so just treat it like a constant. And the derivative of r would just be 1 dr dt. It's not 2 pi plus r. It's 2 pi times r. Think if you have 3x, what's the derivative? 3, right? Same thing here. 2 pi r, the derivative's 2 pi, but then you need a dr dt, okay? And then what do I need to do at this point? Plug in. I know that my dr dt is 0.75, so I have my dc dt is 2 times pi times, I'm going to write that as 3/4 so I can use my mental math here. So I end up with 1.5 pi. Does that seem right? So what does it come to as a decimal? Sure, 3 pi over 2 would be fine. Or if you do it as a decimal, it's like about 4.712. Does that look right? Okay. Now, the other thing here that some people have trouble with is labeling. Okay, the labels aren't as hard as they might seem here. So if I'm trying to label this, think about what the label for circumference is. What would be the label for a circumference? Circumference is just a distance, right? So it'd just be like units. So what's the label for this one in feet? So this would be feet. What's the label of time in this problem? Seconds. So my label would be feet per second. this just makes more sense, you know? So yeah, 3 pi over 2 is exact, but this here probably makes more sense for these type of problems. So I would probably put them in decimal form just so you can check to see if your answer makes kind of sense. So what does that mean? That means the circumference is doing what? Increasing at a rate of 4.712 feet per second. Okay. Questions on that? Does everyone see where all that stuff comes from? Okay, so let's go ahead and look at the next one here. Here we're talking about volume of a spherical balloon. Look at that. Okay, the spherical balloon is inflating or inflated with gas at a rate of 10. So what is that? That's part of my known. So what is increasing at 10? The gas, so what would that be called? Think about the label here, cubic feet per minute. What would be what would be like a feet cubed? Not area, but volume. Okay, this is the volume of the balloon. Okay, so I would call this a dV dt. Right? If you're pumping air into the balloon, the volume's getting bigger, isn't it? So dV dt would be 10 because it's getting bigger by 10. How fast is the radius? So what I'm trying to find is what? Yeah, dr dt. At the instant when the radius is 1. So I'm going to say find dr dt when r equals 1. And then we'll do the when r is 2 in the next step here. So this is just part A. So first thing I need to do is find an equation that relates my volume and my radius. So of a sphere, do you have that on your sheet there?
We do.
Your volume is what? And then what do I do with that? The derivative. What's the derivative of v? dv dt. And then the 4/3 pi just hangs out front. It's just a constant there. What's the derivative of r cubed? Good. It will. Okay, so then you can clean this up a little bit, like the 3 and the 3 down here would cancel, right? Because you'd have 12/3, which is just 4. So those you can cancel here. And then what am I going to do once I'm to this step? Solve for dr dt. So I'm going to plug in my values here. So what can I plug in for dv dt? 10. So I have 10 equals 4 times pi times what's r squared? 1, because it's 1 squared, right? My r is 1. And then dr dt. So how do I get dr dt by itself? Divide by 4 pi, because that's what this multiplies to. So 10 over 4 pi would reduce to 5 over 2 pi if you wanted it that way. Does anyone have that as a decimal? 7.854. And what would be the label for that? Think about, we're finding dr, which is a radius per time, feet per minute. Perfect. And if you're going to round them, which, you know, makes sense to with these problems, just round to 3 decimal spots, okay? So any questions on part A here? So if I need to do part B, I just need my r to equal 2, right? So do I need to redo the derivative? No. What do I need to redo is just plugging them into here. Yep. I have no idea. I just was listening to them. But yeah, that's not even close to right, to be honest. Yep. This here actually is not right. Thank you for pointing that out here. This is a very, very, very common mistake. you need to put 2 pi in parentheses if you're going to divide by it, because otherwise it does 5 divided by 2 and then multiplies by pi. Because this is like 5 over 6, which would be point something. What'd you get? 0.796. There we go. Thank you. So yeah, be very careful of that, especially with one calculators. It's really hard to see that you're not doing that right. The more high-tech calculators, it's almost like cheating, you know. It shows you that the pi's in the denominator or numerator. I know. Okay, so let's go on to part B then. So for part B, we're plugging r equals, what was it, 2? Yep, 2 feet. And I can just take it from this step right up here and plug in all this stuff again. So has my dV/dt changed? No, it's still 10. So I've got this. Whoops, that's a 4 because the 3 cancels. So 4 pi. And my r squared is going to be 2 squared, right? So what am I going to divide by this time? 16 pi. So I just divide by whatever this amount is here. And then just be careful you put that in parentheses here and we'll get there. What are we getting? 0.3. Okay. So 0.199 if we round to 3. And it would still be in feet per minute, right? Or you could write it as 5 over 8 pi. That's the same. What? So the radius should be getting bigger as they're inflating the balloon, right? So that makes sense that it's positive and everything there. So any questions on those two? Okay, let's go to the back. Okay, moving ladder. This is a very common type problem for these type of questions. Okay, so we've got a ladder leaning against a house, so we need a picture here. So I'm going to have my beautiful house over here, and I'm going to have the ground down here, and then I'm going to have this amazing ladder here. Huh? It just starts falling. Yep. Okay, so we've got this ladder leaning against a house. So it forms this nice right triangle, doesn't it? Okay, it says a 25-foot ladder. Is the length of this changing? No, this is staying 25. So you can write 25 there. Okay, you can use 25 in the entire problem because that's not changing. Okay, when things are changing, you can't plug them in until you take the derivative. Okay. So 25-foot ladder is leaning against a house. The base of the ladder is pulled away from the house. So this is moving in this direction, right? And that rate is 2 feet per second, so we'll use that in a second here. How fast is the top of the ladder moving down the wall? When the base is 7 feet, 15 feet, and 20 feet, 24 feet from the house. So what we need to do is we need to create variables for these two spots. So whether you're going to use x and y or a and b or whatever, let's just use x and y. And now I need to start with my, known and what I'm trying to find here. So it's known that it's being pulled away from the house at 2 feet per second. So what is that rate going to be denoted as? dx dt, right? Because this one is being pulled away. So my x is increasing at that rate. So my dx dt would be positive too. How fast is the top moving down? So what am I trying to find? dy dt. Should it be positive or negative? Negative, because y is getting smaller, right? So when I'm done, I probably should get a negative for that. So find dy dt when the base is 7 feet. So when what? x equals 7. Good. So any questions on the setup of that one? Does that kind of make sense? Okay. So now let's go ahead and try the problem here. So I need something that relates x and y to each other. X squared plus y squared equals 25. That's 25 squared, right? So that sounds good to me. Okay, once I have that equation, what do? Take the derivative. What's the derivative of x squared? 2x dx dt plus 2y dy dt equals? I take the derivative of it. 0. Right, it doesn't, you can multiply that out if you want. It doesn't matter what the number is. It's going to be 0. So that's why I didn't even worry about it there. Okay. So any questions on this derivative here? Okay, so now I'm going to start plugging things in. We're going to run into a little problem. You'll see it in a second here. So if I'm plugging things in, what do I plug in for the x? 7. So I'm plugging 2 times 7, and my dx dt is 2. Plus 2 times, can I plug anything in for y? No, so I've got y. Can I plug anything in for dy dt? No. So don't I have 2 different variables to solve for here? That's an issue, isn't it? Yeah. So we have to figure out a way to come up with what my y is equal to. Don't I know at this very instant that my x is 7? Okay, when your x is 7, isn't your y something? Because this is a 7, this is 25, so can't you find what y is at that instant? So if x is 7, go ahead and find what y equals. So we get 24. And then you can plug your 24 in for this spot here. And then you can go ahead and solve for dy dt. Okay? So we get negative 28 over 48, which I have negative 7/12. I'm not sure what it comes to as a decimal there. 0.5835, so 0.584. And it should be negative, which it is, right? And what would be my label for that? Feet per second. And then just make sure that you answered the question. So let's see here. How fast is the top of the ladder moving down the wall? So if I'm answering how fast is it moving down the wall, I would say it's moving down the wall at a rate of 0.584. Okay, it's not moving down the wall at a rate of negative 0.584. The negative implies that it's going down. Okay, so let's just answer it for the first one here. So moving down the wall. At a rate of that. Now, did I actually finish the whole question here? No, I still have to do when my x is 15, right? So go ahead and try when x is 15. Now you don't have to redo the entire problem here because I already have my derivative, right? So I'm still using that same derivative here. Oops. That's not what I wanted. Oh gosh. We're just going to move this guy. Okay, so you're still using this derivative, and then we're using when my x is what for this one? 15. Can you find what your y equals when x is 15? Yeah, and you're still using the dx dt is equal to 2, right? And then go ahead and solve for dy dt. So see what you get for part B, and then we'll write the answer here and compare. Here. So we get y is 20, and then you plug those in. What did we get for our dy dt? And does that reduce? Negative 1.5, and that would still be in feet per second, right? And you could still answer that, so it'd be moving down the wall at a rate of 1.5 feet per second, right? Okay, did anyone do C yet? Yeah. Okay. So for part C, same idea. When my x is 24, what's my y? 7. They just switch, right? And when I plug it in, what do I get? 6 point what? 857. And that's in feet per second. So does anyone have questions on how to do those? Okay, so last example here, an accident at an oil drilling platform is causing a circular oil slick. So it's perfectly circular, okay? The slick is 0.08 feet thick. So that number we're probably going to be using for something. And when the radius of the slick is 150 feet, wow, I really butchered that here. The radius is increasing at a rate of 0.05 foot per minute. So at what rate in cubic feet per minute is oil flowing from the site of the accident? I know, it seems like a lot. So let's try to organize it here. Our known. Okay, so we know, let's see here, my dr dt is 1. 0.5. So that would be this one down here. So that's taken care of. And I know the radius is what? So, whoops, I forgot to put the 0.05 or 0.5. So my R is 150. Can't write here today. And then we got to figure out what we're trying to find. At what rate in cubic feet per minute? So if we're talking about cubic feet, that would be what kind of a rate? Volume. So we're trying to find the volume, the rate of the volume. So that'd be dV dt. So I have to relate volume and radius together. So this is pretty tough, right? So we have we have the circular oil slick on the water, right? And it's got a little bit of thickness to it, which is why it's a volume and not just an area, okay? What's the height of this circular 0.08? Okay, so that's the height of this. So how do I find the volume of a circular cylinder? I take the area of the base and I multiply by the height. So the area of the base, isn't the base a circle? How do you find the area of a circle?
Pi r squared.
Okay, so I've got pi r squared. And then I multiply by the height. And what's the height of this? Yeah, but what's the height of this particular one? Isn't it 0.08? Right? Oh, okay, I didn't hear you say it. Okay, I'm just going to pull that 0.08 out front so it's easier to do the derivative. And then what do I have to do before I start plugging things in? Okay, so if I take the derivative, this would be dV dt. What happens when I pull the 2 down here? It turns into 0.16 pi. And then this would be r to the first, and then what do I need in the back? dr dt. Okay, then I know my dr dt is 0.5, so 0.5 is going to go in this spot. And I know my r is 150. So can I solve for my dv dt now? Yeah. So go ahead and see what you get for dv dt then. Should be like 37 something. 37.699. And what would be the label? It even tells you in the problem. Cubic feet per minute. So feet cubed per minute. Yeah, we have to find our homework.
It's on the next page.
There you go.